Yeah.
Or whatever as a simple boundary representation.
So we are very happy to have Antony Speranza today, who will tell us about generalized entropy and quantum gravity. Please.
Okay. Yeah. Okay. So thanks a lot for having me here. Yeah. So as mentioned, I'm going to be talking about generalized entropy for subregions in quantum gravity, and this is on this work that came out last June with Kristen Jensen and John Source. Okay, so just to kind of set up the broad overview, so generalized entropy is a quantity that was introduced originally in the context of black hole thermodynamics. It was introduced by Bekenstein as a way to kind of save the second law of thermodynamics from throwing entropy into a black hole. And so the proposal was that if you have a black hole, you have entropy outside, you could in principle decrease the entropy outside by throwing it in a black hole. But if you then associate an entropy for the black hole itself, given by A over 4G, the total quantity is supposed to satisfy a second law and always increase to the future. So more generally, in various applications, involving holography, say Ryutaki-Yanagi formula, people have started to appreciate that generalized entropy is something that you can associate with more general surfaces in quantum gravity. So if you think of some codimension 2 surface that I've drawn here in red, you think of that as bounding a subregion that's kind of the causal development, and there's some system associated with the inside of that region. Say you wanted to write down an entropy for that region. It turns out the generalized entropy in semiclassical quantum gravity is a useful quantity there. And the reasons it's useful is that there's arguments that this thing is UV-finite. So even though entanglement entropy in quantum field theory is kind of famously divergent, there are arguments that the divergences in the entanglement entropy cancel against similar divergences coming from renormalization of Newton's constant. And so generalized entropy is supposed to be a well-defined UV-finite quantity. And it's also, you see it nicely relates the geometry of the spacetime captured by the area here to the entanglement entropy. So it's a quantum information, a relation between quantum information and geometry. So some of the applications, as I already mentioned, it shows up and it was originally introduced in the context of the generalized second law in black hole thermodynamics. More recently, sort of upgrades of things like the Bekenstein bound lead to the semiclassical quantum focusing conjecture. Generalized entropy shows up in entanglement entropy and holography via the Ryutaki-Yanagi formula and quantum extremal surface formula. And related to this, it's also behind kind of this key player in these derivations of the Einstein equation from entanglement. And so you can do that either in holography or sort of goes back to the older stuff by Jacobson, where you derive Einstein equations from thermodynamics. So this is going to be, the generalized entropy is kind of the focus of the talk, and part of what I'm going to be talking about is trying to understand some recent works where you're interpreting this entropy as an actual legitimate entropy associated with an algebra in semiclassical quantum gravity. Switch, okay, yeah. So just to review where some recent ideas motivating this have come from, it really grew out of these considerations of applying the theory of von Neumann algebras to trying to understand this generalized entropy. So probably the thing that kicked it off was this recent work by Leuhäuser and Liu, where they were looking at these strict large N limits in holography. And they argued that you get these emergent, what are known as type 3-1 algebras coming from a CFT at finite temperature in a large N limit. And they wanted to interpret that since, as we'll discuss throughout the talk, type 3 algebras are these things associated with subregions in quantum field theory. They wanted to interpret this as the emergence of the bulk spacetime and the exterior of a black hole. More generally, they said there should be emergent type 3 algebras. If you write down a bulk geometry, you can write down subregions, and that they argued that there should be more general emergent type 3 algebras showing up in these large N limits in holography. And the thing that was really interesting is sort of this is like the strict infinite N quantum field theory limit. But then there was this work by Witten that showed where if you take into account a specific kind of gravitational back reaction coming from 1 over N corrections to the story, it deforms the algebra to what's known as a type 2 algebra, which is important because it possesses a well-defined notion of entropy. So entropies are kind of not very well defined for these type 3 algebras, but there's a sense in which they work for type 2. So that's something we'll be discussing throughout the talk, but this was something that I found very interesting, is that you can really write down an algebra with a well-defined entropy. And it seems to explain why you're getting these finite results in that were argued from this cancellation of divergences in the generalized entropy. So I've listed some various subsequent developments talking about how various situations where you can see this type 2 algebra emerging. The specific one I wanted to highlight is a work by Chandrasekaran, Longo, Pennington, and Witten on describing an algebra for the de Sitter static patch. And I'm just highlighting it because the way in which they obtained the algebra is sort of the framework that we're going to be following in this talk for trying to describe more general subregions. So as I mentioned, I've mentioned in the previous slide, these initial works were usually for backgrounds that had a specific boost symmetry, so things like ADS-Schwarzschild and the de Sitter static patch. And that was important to arrive at this relation between the algebraic entropy that was written down in the generalized entropy. And the goal for this talk is to note that, you know, these generalized entropies have been argued to be well-defined for generic subregions in quantum gravity. So we would like to see if we can generalize this construction of gravitational algebras to get these type 2 algebras for subregions. And so that's the goal. The result is we're going to argue that indeed you can write down type 2 algebras for generic subregions in semiclassical quantum gravity. And as a subclassification, we'll discuss these situations where you get these type 2-1 algebras for bounded subregions, which are the analogs of like the de Sitter static patch. If you think of it, the de Sitter static patch is kind of a finite region in spacetime. Whereas for regions that are kind of the exterior of such bounded regions, so analogs of the exterior of a black hole, will argue that there's these type 2 infinity algebras. You should think of what that subclassification means is that in the type 2-1 case, there's a maximal entropy state, whereas in the type 2 infinity, there's not a maximal entropy state, but in both cases, there's a well-defined entropy. The second thing we want to argue is that, okay, these algebras have an entropy, but this entropy can be associated with this semiclassical generalized entropy, kind of crucially up to an overall constant. And this constant is somewhat unavoidable because we're not doing sort of non-perturbative quantum gravity, we're really doing this semi-classical limit. And in some sense, these entropies behave a bit more like classical entropies where you can't fix, you know, there's not an actual state counting interpretation, but otherwise it's a useful information theoretic measure. And the final thing is related to these type 2-1 algebras. Because these algebras just have a maximal entropy state, it sort of gives an algebraic interpretation of this entanglement equilibrium conjecture by Jacobson, which was related to algebras in semiclassical quantum gravity for small causal diamonds. And so we'll discuss that this structure kind of naturally explains this feature in this entanglement equilibrium construction. And so the thing that we're going to be following is this CLPW construction for the de Sitter static patch, and we want to go over what you need to do in order to generalize those arguments for generic subregions in quantum gravity. Okay, so that's like the overview of where we're trying to go. So if you have any questions before we get started on any of it, feel free to ask throughout the talk. Before we go into the construction of the gravitational algebras, I'm going to spend a little bit of time just describing von Neumann algebras, just because they can be sometimes a bit unfamiliar. So hopefully I can tell you a few things that explains what they are and why they're showing up in this construction. Okay, so the way I like to think about what von Neumann algebras are and what they're good for is that they're the appropriate language to talk about subsystems in quantum mechanics and quantum field theory. So just have that in the back of your mind and we'll try to justify that statement. But the idea is you're always working with bounded operators acting on some Hilbert space H. And the generic construction is, say you have a set of operators, say some list of operators that you would say you want to say these operators characterize the subsystem I'm interested in. You could say this is like the spin on a single qubit, or it might be the quantum fields localized to a subregion. And you want to say, what are the operators that are, in a sense, independent of the operators associated with my subregion? And those are just given by all of the operators that commute with your set of operators of interest. And so basically the statistical properties of these commutant operators are unaffected by the statistical properties of the original set. So that sort of tells you how to describe the complementary system. The von Neumann algebra generated by your subsystem is you kind of add in additional operators so that you have everything that commutes with this independent system A0 prime. And so the idea is you always start with some system of interest, you take this double commutant to add in all of the other operators that commute with the independent system, and that defines your von Neumann algebra. So yeah, as mentioned here, if you go through this now and keep taking commutants, you can pretty easily work out that you're not going to add more if you do this procedure again. And so the defining condition is that the algebra is equal to its own double commutant. So if you started with A0 and did the double commutant, got the same thing back, then that thing is a von Neumann algebra. And you can view that as a completeness condition for your subsystem. It's saying that you basically have all of the operators that form like a information theoretic like closed system.
Is there an
yeah.
example? Is there an example of something that is in the von Neumann algebra that's not in the original A0?
Yeah.
Sorry. Oh, sorry.
Why is not A0 double prime equal A0?
It's just I could have started with something that wasn't an algebra. So the simplest one that you should think of 2 qubits. Okay, yeah. So you have 2 qubits. I could take A0 just to be the spin X on the first qubit and the spin Z on the first qubit. It's just a finite list of operators. So obviously, if I take products of those, I'm going to get Y, which wasn't in my initial list. But if I do this double commutant construction, I will see I get all of the matrices acting on the first qubit. So yeah. And it's kind of nice, actually, if you start with any set, something you can work out pretty easily is that this A0 prime automatically satisfies this condition. And it's something that easily you can work out. So it's if you start with any set and just take all the operators that commute with that set of operators, you're always going to get a von Neumann algebra. So in this example, you'll just get all the matrices acting on the second qubit. Yeah, and so there's this famous double commutant theorem. We're not going to really use it, but it's important for a different interpretation for what this double commutation thing means. It means that this algebra A is closed in this weak operator topology. So that's the topology generated by basically demanding continuity of matrix elements of operators. And so you can equivalently say if you have an algebra that has all weak limits, that's the same thing as satisfying this double commutant condition. And the last thing I wanted to emphasize is that this is definitely an information theoretic construction in the sense that von Neumann algebras really are giving you stuff that tells you, things, it tells you properties of the algebra just coming from them being operators acting on a Hilbert space. It's largely insensitive to detailed dynamics or symmetries or things like that. So you do want to think of it as really an information theoretic type construction. Okay, so as the simplest example that you should be quite familiar with is the case where your Hilbert space comes as a tensor product. This is known as the type 1 case. So here we just have a Hilbert space that's the tensor product of 2 different Hilbert spaces. The first algebra is just all operators acting on the first factor. The commutant is all operators acting on the second factor. But the point of the type classification in von Neumann algebras is that this is not the most generic thing you can do. So in infinite dimensions, there's other ways to satisfy this double commutant theorem without assuming a tensor factorization of your Hilbert space. So just to review what these different things are. So one of the things that's important to keep in mind is this type classification says there's different ways to satisfy this, but then it also tells you certain things about information theoretic properties of the algebra you're dealing with. So in this type 1 case where you do have the tensor factorization, basically you have all of the things that you're used to from quantum information. So you have things like density matrices. You can always form states, which are just ways to take expectation values of your operators in your algebra. As we'll discuss, you have something called a modular operator, which is important in situations where you don't have density matrices. It's sort of a replacement that we'll see is there for all of the algebras. And then you can have traces defined. You can talk about entropies associated with density matrices, and you have nice things like relative entropy. So lots of information theoretic measures as well. So the type 3 case is the one is a little different. It's the one that you would get from operators of local fields in quantum field theory. So this is when you restrict a subregion and you ask about all of the operators localized in a subregion. These algebras have been argued to be type 3. So in this case, there's no natural tensor factorization of the Hilbert space. You don't have a good notion of density matrix. But you always still have traces, well, not traces, you have states and modular operators. So states just say I can take expectation values of operators in this, of quantum field theory operators. And this modular operator, which is roughly like the density matrix times the inverse density matrix for the commutant, also exists. But in this case, you don't have traces, and that means because you don't have traces or density matrices, it means this entropy is not really well defined. And this is just the statement that von Neumann entropies in quantum field theory are UV divergent. On the other hand, you have a very important concept in quantum field theory is that there is a well-defined relative entropy, which is roughly like a free energy difference between two states. So you can have relative notions of entropy, but there's not an absolute notion of the entropy for a single state. So the goal for this talk is to argue that in gravity, semiclassical quantum gravity, you're in this intermediate type 2 situation. So for these algebras, the Hilbert space still doesn't have a natural tensor product decomposition, but apart from that, you have most of the other information theoretic things you would want to talk about entropies. So there is a well-defined entropy or density matrices in this case. As always, you always have states and modular operators. And the important thing is that there is a nice trace. It's related to the fact that you have a density matrix, and from the density matrix and the trace, you can write down a von Neumann entropy. As always, the relative entropy is defined for all types of algebras. Yeah, so this chart is just to show you what we're going for. We're trying to argue that in gravity, the algebras are type 2. And what that means is I have a well-defined entropy. This entropy, again, has a specific interpretation because this trace is not the usual Hilbert space trace, which we'll discuss. So these entropies are something like entropy differences in the type 2 case, and they're a bit more like classical entropies, but it's an improvement over the type 3 case where a lot of these things didn't even seem to be well defined. Okay, so that's where we're going. Well, that's the intro to von Neumann algebras. The goal from here is now to argue that the type 2 algebras are the things you get in semiclassical quantum gravity. Okay. So what is the setup? So semiclassical quantum gravity in this talk will mean the G Newton to 0 limit of quantum gravity. And you expect in this limit that the leading behavior, what this does is it suppresses gravitational back reaction. And so the leading behavior should be captured by quantum field theory in curved space-time. So the setup I've depicted here is that we have, we want to say we have a subregion depicted in blue called S. That you can think of as, say, the causal development of a partial Cauchy surface, which I've denoted sigma. And we want to be talking about the gravitational algebra of fields in that region there. So then the complementary region is denoted in red. And so that's the things out here. And so in the quantum field theory and curved space-time description, you have an algebra of fields associated with the region S. And then the commutant are all the fields associated with this causal complement here. So this is known as Hogg duality in quantum field, axiomatic quantum field theory.
So
Yes.
the boundary, the sigma is at finite distance?
So yeah, so the setup I'm going to be considering is like sigma, the blue region is kind of like think of a causal diamond, it's a compact region. And then I'm going to be taking the complementary region to include an asymptotic boundary. You can do it where you could be working in a closed universe as well, where the complementary region is also compact as well. But there's various ways. The nicest, I like to do it where one region is local and the other region is asymptotic because you see the difference between the two in like a single sweep, but you can do both in any combination. So the two-sided black hole is two asymptotic regions, for example. Okay, so these quantum field theory algebras act on a Hilbert space. It's the same Hilbert space HQFT, and so you don't assume that there's a tensor factorization associated with the subregion and its commutant. And it's crucial that these algebras include also the graviton degrees of freedom, but in this limit, as G Newton goes to 0, those are just massless spin 2 particles. So really the interactions are completely suppressed here. And as mentioned, these algebras are type 3-1, which means they don't have good traces or density matrices that are sort of defined in a regulator independent way. So the gravitational, basically the difference between the quantum field theory and curved spacetime and the sort of quantum gravity description here is that we want to incorporate some aspects of the gravitational back reaction. And these come about from requiring that the system satisfies the gravitational constraints. So when you go to embed basically this quantum field theory description into the interacting theory, you need to make sure that the constraints are satisfied. The constraints arise in gravity due to diffeomorphism invariance, and you can think of constraints as operators that act on a kinematical algebra that generates the action of gauge transformations. And so what we want to do for having a gauge invariant algebra is start with this kinematical algebra and ensure that the constraints act trivially. So you want to find operators that commute with this constraint generator. So some of these, often you can satisfy constraints by just, appropriately gauge fixing your description. But essentially what's happening is that, any complete gauge fixing is necessarily going to be partially non-local. And so if we set up a gauge fixing where we can say, I have a well-defined algebra associated with a subregion, and it's not, the gauge fixing doesn't include some weird dressing to the exterior region, such a gauge fixing is always going to be incomplete, just because a completely, gauge invariance in some sense a tension between locality and a description in terms of the fundamental degrees of freedom.
So should we be worried about diffeos that move these regions into each other?
You should, yes, you should be worried about all the constraints. So the goal, basically the prescription, the picture I have in mind is that some of these you should be able to handle by just, gauge fixing. So I say I've given a prescription to define where the subregion is. And then what I'm saying is even after you do that and you write down operators localized in the region, you set up a coordinate system in the region, you set up one in the red region, the outside, there's still going to be constraints coming from sort of the difference between those local coordinate systems. So in particular, the reason we're going to be focusing on this boost constraint here is that there's kind of a notion of time for the subregion, and there's a separate notion of time for the exterior region, and this local gauge fixing sort of doesn't relate those two. You can sort of have a kink in the time from one region to the other. By imposing this constraint, you're ensuring that that's sort of consistently imposed in both diamonds.
So what class of vector fields are you going to allow?
We're going to be talking about a single vector field in this talk. And so to describe which vector field it is, it's going to be a vector field that looks like a boost. What does that mean? It means it vanishes at this codimension 2 entangling surface, and we want it to preserve the light cones at that entangling surface, which means, okay, this condition here that
More generally,
Yeah.
So you have some entangling surface, which is codimension 2.
Yes.
And the condition you want to impose is something like the normal components of the vector field have to vanish on the entangling surface.
So the vector field vanishes, it fixes the entangling surface.
But why can't I allow diffeomorphisms that just move me around the entangling surface?
You could, and so what, I might describe that later. So the short answer is you probably should do that. It's going to be related to
Spatial diffeomorphisms of the entangling surface.
yeah, it's going to be where you'll see how we're going to do this in a second. Roughly, it's going to be related by so if you think of the asymptotic region, what we're doing is kind of including the ADM Hamiltonian. The thing you're saying is also to include roughly things like angular momentum generators. So there is it's not like fully worked out. There is aspects where you start adding additional constraints associated with things like rotation. The statement is it probably doesn't change the type of the algebra, but in the details, you know, this thing about getting these type 2 algebras and well-defined traces seems to be related to this boost generator. And so we're going to focus on that, but I think a future work is to probably keep adding more degrees of freedom associated with the rotations. So I'll try to point that out when that comes up. But yeah, so just to state what this vector field is, you need it to vanish on the entangling surface, and its covariant derivative at the entangling surface needs to be proportional to the binormal. And we're going to this proportionality constant we'll call the surface gravity for this vector field. We're going to take that to be constant on the entangling surface, and we'll try to describe why this is the relevant vector field, at least for what we're doing in this talk. Yeah, and again, by being proportional to the binormal really means that it's preserving the light cones at the surface there. Okay, so in order to get an algebra that's sort of non-trivial, if you think, at least in standard setups where this vector field in the background is a killing vector, if you just look for all the operators invariant under global time translation, you pretty quickly say, okay, I eliminate basically all of the operators in the algebra. And so this is where you need to introduce this extra degree of freedom that we call this local observer for the subregion, or you add an asymptotic boundary. And you should think of these as kind of objects that you are dressing the local fields to. So the observer kind of defines somewhat loosely where the region is and how you're dressing operators to it. For the outside region, you can just take the asymptotic boundary as to be the dressing surface. But then you add in the total energy of the space-time captured by the ADM Hamiltonian. So this seems to be necessary in order to get these well-defined type 2 algebras. And the way that we'll couple these observers or the ADM Hamiltonian is that you initially introduce them as independent degrees of freedom. So we tensor in a Hilbert space and we have them act on that Hilbert space, which we take to be L2 of R. So the observer Hamiltonian is just going to be taken to be the position operator, and the ADM Hamiltonian will be the position operator on this other Hilbert space. And the total gravitational constraint associated with this vector field, since sort of all energy has to gravitate, these Hamiltonians show up in the constraint, and it's given by this equation. So if you work out where the vector field's pointing to the future and the past, you'll write down this is what the constraint implies for that flow. The important thing.
Should we be concerned that these Hamiltonians are not are unbounded below?
Yes. Yeah, so I'll mention that point first. So as mentioned, these Hamiltonians are not bounded from below. The way you can treat that is that really they should be acting on L2 of R plus as opposed to L2 of R. In practice, what you can do is add that as a constraint as an end at the end. So you can basically project onto the L2 of R plus. Since that projection is going to be in the algebra, it commutes with the procedure of imposing the diffeo constraint. So we can do it in either order roughly. And so we'll do the constraint for the boost first and then impose the positive energy as an additional restriction. The second thing is that these Hamiltonians, the other important thing besides being unbounded below, they also have a continuous spectrum. And that's why you can represent them as the position operator acting on the Hilbert space. So spectrum there is the full real line. that ends up being technically important for the construction of the algebras. And I think it should be interpreted as, again, that you're in this semi-classical limit where you're not resolving basically discrete energy eigenvalues of the full quantum gravity description. So I think you should view that as a semi-classical,
So
just
if
assumption.
the original goal was to define some sort of notion of states and traces, density matrices and entropies, et cetera, that are associated to the causal region.
Yes.
Then this introduction of an observer that you're going to address things to seems like
Extraneous. Yeah.
extraneous. So, but
Yeah.
you can say, okay, let me give up extraneousness for needing to do it. But then I would want some sort of equivalence relation that would say, if Bob defines his set of observables and entropies and so on, and I define mine, that there's some equivalence between those two things. So it's like you introduce some extra degree of freedom, but an equivalence relation that says they're really all the same. So is there going to be some notion of that sort? That if I consider two different, clocks that I'm going to address things to, that I get the same.
There's somewhat of a version of that. It's not going to be exactly probably what you're, so I'm not going to tell you too much about what the observer actually is. It just needs to be something where this Hamiltonian is integral of the observer stress tensor, and it needs to be like effectively decoupled from the quantum fields. There is a separate notion that you could just say it kind of depends on how I pick the flow of time throughout the entire causal diamond, which might be one version of what you just said.
Oh,
So
I was just thinking about, okay, there's some integral curves of this of your Hamiltonian. If you have some nice situation where there's like a boost isometry, et cetera,
yeah,
then I could just consider different observers that are in different spatial locations traveling their own,
yeah, all following the Killing vector, yeah.
Yeah, so.
But in this setup, we don't have a natural notion, but there is a really nice equivalence relation of the form when there's no natural notion of time translation. It's not going to be in the slides, but roughly there is, you could just say, weight this vector field in a slightly different way by picking those observer world lines to be different. These will correspond to essentially changing the generator of the Hamiltonian on the quantum field. So that's what this HCG is, just the generator of these translations on the quantum field. It'll show up as you write down sort of a different state, which we're getting ahead of ourselves, but there's a way to construct the algebra from this. You write down a different state to construct the algebra, but there is sort of a well-defined notion that if you use two different states, you get, there's a unique unitary between the algebras that you construct. And the entropies at the end of the day, when you express them as generalized entropies, agree. If you did the two different states. So there is a sense in which there's sort of some frame dependence to the construction, but it's sort of, there is a relation of the form you mentioned.
Okay.
Just to give the terminology, it's related to the existence of these cocycles that relate different modular flows. So, yeah.
Is it going to be important for your construction that you included both the ADM mass and the observer, or could you get away with one or the other?
It's technically important to introduce both, yeah. You're not gonna really see it here, but the details for how you impose the constraints on the Hilbert space don't work really when you only have one, roughly. So you kind of, yeah. Yeah, I can maybe tell you more details later or afterwards, but yeah. So just to describe what the Hilbert space is, we have this kinematical Hilbert space that consists of the original quantum field theory Hilbert space, and then these two additional Hilbert spaces that we've added in with the observer and ADM Hamiltonian. We're eventually going to impose the constraint on this. And then this kinematical algebra that consists of the quantum field theory algebras generated by local fields and the ones on the inside and the outside, and then the full set of operators acting on these two Hilbert spaces. So you get the gauge invariant algebra by imposing this constraint that I wrote on the previous slide. And if you go through some of the details on how to impose that constraint, you find that you can actually represent the algebra as just acting on the first two factors of this Hilbert space. And the algebra associated with the subregion consists of operators that commute just with this C, the quantum field theory generator and the observer Hamiltonian, roughly because, you know, if it commutes with these two, the quantum fields were already defined in the kinematical algebra to commute with the ADM Hamiltonian before imposing the constraints. So the procedure is you look for things that commute with this operator when you represent it on just the first two factors here. Okay, so to determine what algebra you have that commutes with this operator here, this is a simple undergrad quantum mechanics problem to just work out that the operators that commute with this take this form where you kind of twirl your original quantum field theory operator by these e to the I ph. So p is just the conjugate variable to q, so they satisfy p with q is I, and then of course the original q is going to commute with this because it commutes with q and it was defined to commute with the quantum field theory. So these operators generate the algebra associated with the local quantum field theory. And the commutant algebra, note that this thing kind of was constructed as a commutant. We said we wanted everything that commutes with this guy, as well as the quantum fields in the complementary region. So that's how you know it comes to you as a von Neumann algebra. And then so the commutant is this operator here that we started with, and then the quantum fields in the complementary region. So just to say, this form of an algebra is what's known in the von Neumann algebra literature as a crossed product. Roughly, this is something anytime you have a group acting on your algebra, it's a way to take your original algebra and add in the group generators to construct a new von Neumann algebra. And so you can see that Q, when it acts on this, is going to generate the action of H because of how it commutes with the P in that equation. Okay, so far we've said that imposing the constraints on the quantum field theory algebra coupled to the observer and ADM Hamiltonian gives us this cross product algebra. So, but it's still with respect to this flow generated by this Hamiltonian HC. We still need to determine what the algebra type is. So the claim is, in order to answer this question, the claim is that this operator, this boost generator on the quantum fields actually generates what's known as modular flow with respect to some state for the quantum field theory algebra. And this implies that A is type 2. So just to argue for what this is the first time we've encountered what these modular operators are. So you should think of a modular operator as, you can think of it in terms of density matrices by this equation, where it's like the density matrix for the subregion times the inverse density matrix for the complementary region. And this is in quotation marks because this is only true, say, in the type 1 and 2 cases. So this isn't literally true in quantum field theory, but it's something we do often when working with density matrices regardless. So these two guys are a bit UV divergent in quantum field theory. The modular Hamiltonian is just the log of this modular operator. It's this sort of difference of the logs of the density matrices, and it generates a flow. So e to the ISH generates what's known as modular flow. And in the type 3 case, this modular flow is an outer automorphism. The situation that you should have in mind, just one second, I'll finish the sentence, is in the Rindler, in the Minkowski vacuum in Rindler space. This modular operator really is the boost generator. So more generally, you can talk about modular operators for arbitrary subregions, but okay. Yeah, there was a question.
What do you do when like some of the matrix elements are 0 for the density matrix, like rho prime, because you're involved?
Oh, so technically you do modular theory. You're always working with cyclic and separating states, which in terms of density matrices, it means that rho has full rank and rho prime has full rank. So you always work in representations in states where that's true for modular theory.
I see.
So there are no zeros when you're doing modular theory, yeah.
But that might not necessarily include all the physical ones of interest.
Right, and then you just you don't write down modular operators, you have to think a little harder there, but.
They still work.
But so in quantum field theory in the vacuum, in Minkowski space, the vacuum is a cyclic and separating state. And so that's this Riech-Leiter theorem. Okay, so why should you believe me that this HC, which was generating this boost on an initial slice, is actually the modular operator for some state? Well, the claim is that you actually know how to construct this state. You do this formal split, which is a bit UV divergent, but it's something we're familiar with. Yeah, it's something that we do often if you've worked on entanglement entropy before. And you just construct a state that's thermal with respect to this one-sided density matrix and normalize it with some partition function. Okay, so then if you conjugate by just this density matrix we've constructed here, you can see that that generates the flow of this one-sided guy. That'll agree with the flow of the modular operator because this guy doesn't do anything to the algebra. And so this defines this modular flow. And the important thing is that it satisfies a KMS condition. And here you just formally write it as a trace of the density matrix. And anytime you have a thermal density matrix, this KMS condition that the float operator is related to the analytic continuation with the order reversed. It just follows from the cyclicity of the trace. So this was a form.
Sorry, you're saying this is an arbitrary vector field now with no isometry?
Yes, so it's important that this operator H only generates time translations at an instant in time, basically. And so away from along the flow, since H isn't conserved in the background, it'll be non-local, but initially it is generating a geometric action, and also close to an entangling surface. You should expect it to look pretty close to the boost because it'll look like Rindler there.
So I mean, okay. So you're saying that the action, I mean, the modular flow does correspond in the limit as you're approaching the initial surface.
Yeah, so to fields localized on that surface, it'll look like the instantaneous time translation there. And then for longer times, it'll become non-local because the Hamiltonian's not conserved. So why isn't this just the answer? So the main issue is that splitting this boost generator is a UV divergent operation. And so you have to be careful about what's going on near the entangling surface. And so the insight or the idea is that since, really the modular flow cares about what's happening in the deep UV, so that's the thing that could distinguish it from other types of flow. And that's associated with things close to the entangling surface. And when you zoom in on an entangling surface, you should expect space to locally look like Rindler space. And so you expect this modular flow for basically any state to look like the Rindler boost around that. So that's the intuitive idea. And so as we know, the boost in Rindler space is the modular Hamiltonian of the vacuum. So the version in terms of operator algebras, it's this Bisignano-Wigman theorem. If you're familiar with sort of Rindler space and the thermality of Rindler space, this is also the Unruh effect in Rindler space. So the conjecture is that when we made this choice that H should generate the boost at the entangling surface, that was what you needed to do to ensure that this state exists where there is a modular Hamiltonian generating that action. So the precise relation will be that it's proportional with a proportionality constant beta, and beta is determined by the surface gravity by this usual relation. And this is in analogy to the Unruh temperature here. Okay, so the idea is this is a conjecture. Actually, I have another slide there was a couple of things I wanted to say about this. So I think part of the non-trivial part of this conjecture is this proposed zeroth law, so that I think it's important that this surface gravity is actually constant. And so you could phrase this as the modular flow should look like a boost with this constant surface gravity. So this ends up being important in the entropy computations, but it's something that you could investigate like in quantum field theory.
Sorry, what's determining kappa in Rindler space?
Sorry, I didn't
What's
hear.
determining kappa in Rindler space?
So it's the killing vector. It's It's important that it's not trivial that it's constant. You have to pick an overall scale and you need to tell you where the observer, you know,
So it's just some fiducial reference observer
yeah, so
in his
roughly these, when
near
you,
distance from the horizon.
yeah, so what happens is.
That's fine. You don't need. to
Yeah,
go
you
through-
see, the modular operator always divides out by kappa, so the only thing that's non-trivial here is that it's constant, and then it's always kind of gives you a unit temperature. So it's non-trivial that it is constant along the entangling surface in Rindler space. Okay, I just wanted to flash a few other arguments in favor of this conjecture. There's this co-cycle derivative theorem that says if you ever started with a legitimate modular operator and you deformed it by adding, or modular Hamiltonian, and adding arbitrary elements just from localized in the algebra and localized in the commutant, you can prove that this is actually the modular operator of some state. So the idea is that as long as your flow has the right behavior right near the entangling surface, you can cancel any non-local behavior by just adding these operators from the algebra. We also discussed in the paper a computation of conformal perturbation theory for a causal diamond. So causal diamonds are the other, in conformal field theories, are the other well-known case where you have a geometric flow. And you can check that you can construct this state, this proposed state, using conformal perturbation theory. So you deform a CFT and try to check if you can construct the state there. Also, since Gautam was here last week talking about similar things, I wanted to mention that in their paper, they had an interesting example of a killing horizon, like in Schwarzschild de Sitter, where the two temperatures of the horizons are different. And they kind of have a way, at least I would interpret it as if you look at what the modular flow is, it's sort of, this proposed flow is localized on the past horizons there. And if you think about the geometric flow, it sort of rescales the vector independently on the two horizons so that there is a constant surface gravity between the two horizons for the modular flow. And it's not the same thing as the killing flow. So just to point out a verification of this zeroth law in a situation where you could have expected the temperature to be non-constant. Okay. I'm a little low on time, but okay. Okay, the goal is to now say, let's accept the conjecture and let's see what that says for the algebra, the gravitational algebras that we construct. Yeah, okay, sorry, I must have mentioned. So basically, the statement is if you do a crossed product with respect to modular flow of a type 3 algebra, the statement that Takasaki and Kahns showed is that the resulting algebras are type 2. The way you see that is you can explicitly construct a trace on the algebra and see that it's finite and not sort of UV divergent. Equivalently, you can actually write down a state, you know, of this algebra and explicitly compute this modular operator and see that you can write it as in a factorized form. So the way you do this is, one way to characterize what a modular operator is it's the thing that you would insert into correlation functions to reverse the order like this. This is essentially equivalent to the KMS condition. So modular flow always satisfies a KMS condition with respect to the modular time, basically. So you can write down this algebra that we constructed a few slides ago and consider the states of the form just some arbitrary QFT state tensor, a wave function for this extra degree of freedom, which was this observer Hamiltonian. And you can just solve this relation here using, in principle, elementary, but algebra manipulation. So there's nothing fancy, it just takes a little bit of work and a few Fourier transforms to do this. Okay, so there's a bunch of objects in this that it's not too important. The reason for showing this formula is that to show that there is a well-defined formula that's written explicitly in terms of well-defined operators in the quantum field theory. So these H's are the modular operators for this vacuum state that we discussed on the previous slide, that was this proposed KMS state. And then this delta is this relative modular operator, which is the thing that shows up when you talk about relative entropies. You can get the commutant density matrix as well. These J's are these modular conjugations. They're kind of like CPT operators. But yeah, so I'm just showing you that you can get an explicit formula. So once you have this density matrix here, you can go ahead and try to compute the entropy of this. The last thing just, oh, sorry. Yeah.
And before, when you had written the density matrix, you had this kind of a half time evolution operator, like a time evolution for 1/2. Unless maybe that was a typo or something, but didn't you have a rho psi equals e to the minus beta h, right?
Okay, yeah, sorry. That was in my argument for formally saying that there should be, yeah, I should clarify. This is a different density matrix, right? So I'm not assuming that I split the quantum field theory density matrix. That was just sort of the formal argument to argue for the KMS state. This thing is, say that state exists, then we can work on this crossed product gravitational algebra. And then this is just a different object.
Yeah.
And it's just well defined. It's maybe not obvious, but you can show this is really, this density matrix is in this algebra. And the way, so the reason that this factorization is the equivalent to the trace is a simple fact that if you ever can find an operator that does this find a modular operator for the state, you can immediately write down the trace by just roughly dividing out by the density matrix. So you just define a trace as the expectation value in this state of rho inverse times this. So roughly this, each factor of phi is like half the density matrix. If you divide out by the density matrix, it's like you're doing a trace over the full algebra. So this is just something to keep in mind. If you ever factorize a modular operator, you can always write down the trace. And so this is how you just see explicitly that the algebra is type true. And also just to say, I guess I didn't write this formula. A trace is any linear functional on the algebra that satisfies this equation. A trace of BA. So this is the standard tracial identity. Okay, so what we want to do with this density matrix is try to compute the entropy and relate it to, at the end of the day, the generalized entropy for the subregion. Okay, so the entropy is given by this standard von Neumann entropy formula, trace rho log rho, minus sign. You can also just take the expectation value of minus log rho in the state. So in order to facilitate this computation, you need to make an additional assumption that the observer is not highly entangled with the quantum fields. This is just a simplifying assumption so that you don't have to think about the contribution of the observer's entropy. Well, it's so that you can treat the observer's entropy as a separate contribution on top of the quantum field theory entropy. If they were entangled, it would be a little harder to disentangle or to figure out what is the total entropy in the subregion. So you assume they're not very strongly entangled, and the way you achieve this is you choose this wave function to be kind of very slowly varying. Since Q was the energy variable, the conjugate, if f of Q is very flat, the conjugate variable is roughly the time smearing of everything. And so you're saying you're taking very small uncertainty in this observer time here. So if you plug in this density matrix using this simplifying assumption, you get this formula for the entropy of this state. It involves the sum of a relative entropy between the quantum field theory state of interest and this proposed KMS state. It involves the expectation value of this observer Hamiltonian. There's an entropy coming from just the probability distribution for the observer's wave function. And then this log beta is just a constant additional piece. So now what we want to do is say, okay, we have an entropy formula and we want to say, how is this related to the generalized entropy? In order to do that, if you remember, the generalized entropy involves, UV ill-defined things like the entropy of quantum fields in the subregion. So at this point, you do have to make one of these formal splits and assume that the quantum field theory density matrix factorizes. So if you make that assumption, the formula for the relative entropy is supposed to kind of look like a free energy with respect to log rho. So we assume that factorization, we write down the relative entropy formula. It's given by minus the entropy minus log rho. If you think of this as the one-sided Hamiltonian, this should look a bit like a free energy here.
Or I didn't understand what you meant by factorization here.
So we're now assuming, we're doing this thing where essentially we're saying we've somehow regulated the quantum field theory and can treat the subregion and its commutant as tensor factors, and then we can write down density matrices.
Factorize it.
That's what I meant.
Hilbert
Yeah.
space, yeah.
Yeah. And so that's just, these are these quantum field theory density matrices, because I didn't put the little hats on it, that's the notation. And so those are the UV ill-defined things. But the divergence is supposed to cancel between these two terms because the relative entropy is well defined. Okay, so by using this formula that this proposed density matrix should just be thermal with respect to this one-sided Hamiltonian, you can convert the entropy into this formula. So it involves now the Q of T and observer entropy, and now it also involves the expectation value of basically the total energy inside of the diamond. So then the last step is to convert that total energy into an area term. And this follows from this so-called first law of local subregions. It's basically one of you can use these Iyer-Wald identities to relate the total energy in the subregion to the area of the bounding surface. And so you get this kind of relation using these covariant phase space techniques. Okay, so once you've written this equation down, you use these two terms are what showed up in the entropy. This is what you use to convert the entropy of this density matrix into what now should look like a generalized entropy. We have A over 4G expectation value in this state phi, plus the quantum field theory entropy, plus this observer entropy as well. And the point is, an important point at this step is that this is equal to the generalized entropy up to an overall constant. So if you remember at the beginning, I said I was taking the G Newton to zero limit. The way you should think of this is really this constant, this is really the perturbation of the area around the background value. So really you should use, this constant should subtract off the background value of this entropy term. And there were other constants that showed up, basically log of beta and the partition function when you factorize the Hilbert space for the quantum fields. And that's kind of an unavoidable thing, is that there's always this state independent constant ambiguity when working with these type 2 entropies.
So did I understand that you should really think of the first term as a fluctuation in the entropy away from something?
Yeah, I probably should have written it as delta of A. So it's the order G Newton change in the area over with respect to the background. So I think it's important, yeah. Usually when you do black hole entropy computations using Euclidean methods, or if you can do a microstate counting, you're sort of getting the thing that this piece roughly, or appropriately, you're getting the background value. So these algebras are set up to make sense of fluctuations in the entropy around a background value. And it's.
But in the limit you were working with, that constant was infinity.
Yeah, well, if you think of basically this trace that we've constructed, it's really not a Hilbert space trace. It's roughly like a rescaled trace. So it's sort of, you've renormalized the trace. And roughly that's where this constant comes from. So these entropies you should think of as really as entropy differences, is the interpretation. Okay. Yeah, I'm quite low on time, but I would so I'm gonna have to go quickly, I guess, here. I just wanted to mention that this procedure of converting this generalized, converting the entropy we computed from algebraic techniques into the generalized entropy, this step that we used here is actually saying that the local constraints hold in the subregion. So really there's integral of the local constraints, which you set to 0. And these are the same types of steps that show up in these derivations from Einstein equations from entanglement entropy, where in holography you would say, okay, S-gen is the generalized entropy in the bulk, and then this entropy is the entropy you would compute in the CFT. When you set the two things equal, you see that the Einstein equation has to be holding on the region, bounded by the RT surface. And so you can kind of do a similar thing, is you could say, if I wanted to just say algebraic entropy equals generalized entropy, I can kind of derive the perturbative Einstein equations from this as well.
Is this linearized order or beyond linearized?
Yeah, it's a good question. It's sort of, it's an expansion in G Newton, and it's sort of the G Newton squared contribution. It's sort of the linearized term gives too big of fluctuations. Roughly, you do an expansion in square root of G Newton, and you want to make sure that this has no square root of G Newton term, because it would be delta A over, yeah, anyways, it would blow up. So yeah, the details of what order you're at, it's sort of perturbative in G Newton, but yeah. Okay. In the interest of time, I promised I was going to talk about this, but I'm just going to flash this slide. This positive energy projection that came up, it's important for getting rid of this P operator as a time operator. You're not supposed to have a time operator if you want to have, positive energy. The way this works is that you just project to the positive part of the spectrum of this Q operator. And it has an interesting effect that once you do this projection, this theta then acts as the identity on the projected algebra, and you can compute its trace and you find that it's finite. What this means is that the algebra is type 2-1. And physically what a type 2-1 algebra is an algebra with, well, it's not a finite dimensional algebra, but it's one that has a maximal entropy state. So you can write down this maximal entropy state and this, when you do this projection, and you get this version of this entanglement equilibrium conjecture by Jacobson, which he's argued that small causal diamonds in the vacuum of semiclassical quantum gravity also have a maximally entangled state. In the de Sitter paper by CLPW, this was also an important point, that the vacuum was a maximal entropy state for their algebra. And just to mention, if you do this construction, we've been focusing on the inside here. If you do the same thing on for the outside algebra and do this positive energy projection, the way the signs work out give that this answer is not finite at the end of the day, so it remains type 2 infinity. So the outside algebra doesn't have a maximal entropy state. Okay. So to try to wrap up a bit, I wanted to mention the basic assumptions that needed to go into this to arrive at these type 2 algebras. So the basic assumptions were beginning with that you could do quantum field theory in curved spacetime, and that the local algebras for quantum fields are type 3-1. The second assumption is that you have to add this observer degree of freedom, or a degree of freedom associated with an asymptotic boundary. The third assumption is that once you add those, you have to impose this gravitational constraint, and that's what led to this cross product algebra. And the fourth assumption is that there was this state where this flow generated by this vector field is actually the modular flow for some state. So these four assumptions are what you needed to get the finite entropies. The fifth assumption is this local first law relating the area to the total energy. This is what you need to argue that the entropy you're computing really is a generalized entropy. And then the last step, where you impose this positive energy projection, only comes in constructing this type 2-1 algebra with a maximal entropy state. And so I just listed on the right hand side that all of these things kind of lead to further questions that you can try to argue. Well, you can try to improve the construction, try to see, this geometric modular flow is kind of interesting because it's something you can just check in quantum field theory. It's just a statement about properties of modular Hamiltonians in quantum field theory. There's lots of questions about what is this observer. So what is the interpretation of actually getting it? What can you construct it intrinsically from the quantum fields? Specifically, why did we only introduce this 1 degree of freedom? So that question came up. You can add more degrees of freedom to the observer, as was mentioned, related to kind of the rotational frame. And you can see how that affects the algebras. Yeah, so this is just a list of various ways you could generalize the story. And I'll just mention, I'll have my list of future applications. There's lots of things you can try to do once you've argued that there are these cross-product algebras with well-defined entropies. I guess two I should mention is some work in progress with Tom Faulkner of looking at the generalized second law for black holes. So if you back away from a completely arbitrary subregion, you just look at horizon cuts of a black hole horizon. There's a really nice story where you can use these cross product algebras to, get the generalized second law, but in terms of a well-defined algebra, von Neumann algebra. There's also some work with Gautam and collaborators where you can kind of forget the gravitational story and just say this cross product's an interesting tool. And in particular, you can use it as a regulator for entanglement entropy in quantum field theory. And you can make interesting, rigorous statements about entropy differences. In particular, you can add an extra piece to these proofs of the Bekenstein bound and the quantum null energy condition. Those were like the current proofs. What they do is they convert those statements about entropies into well-defined statements about, say, relative entropies. And so what the cross product can do is actually say, okay, here's a regulator where this really is a statement about entropies or entropy differences. Okay, and then I'll have a few other points to think about in the future, but I guess I'll stop there and take any more questions. So thanks.
Questions?
Yep.
So for general regions, how am I supposed to think about the surface gravity being constant or?
So the statement was this modular flow should look geometric close to the boundary of the region, just because the boundary will look like Rindler space there. And you can ask whether you're boosting at different rates along the boundary. In particular, you could say the boost is related to some other property of the surface, like the extrinsic curvature. And the conjecture is that that's not true, that it's constant on the boundary. And that's important. I can just show you where that gets used. It's important here. So when you use these Iyer-Wald identities, roughly the surface gravity of this vector field shows up here. And if you want just the area as opposed to some funny integral over the surface, you need that to be constant. So it's a conjecture, but it is kind of important for the interpretation of this entropy.
So does that correspond to just saying that, okay, suppose I were to pick my entangling surface to be an ellipsoid rather than a sphere,
Okay, yeah.
then I guess I could imagine engineering this surface gravity to be constant, because if I go to the pointy end of the ellipsoid, I just go a little bit further away from the boundary, and if I go to the fat part of the ellipsoid, I go a little closer, so that sort of the rate at which I'm boosting something along.
Maybe, yeah.
Is that sort of the thing you have in mind? That you just pick where my fiducial observer is relative to the Rindler horizon based on.
Yeah, okay, I see. Yeah, I see. You're saying because the temperature they experience is related to that. Yeah, so effectively you're saying it's the same distance, right? As opposed to depending on the pointing end, right? That's the constancy, I think, right? So I'm saying don't do that, I think.
Okay.
Yeah, so it would be interesting to figure out where this condition comes from. I have a sense in which it might be related if you could do like a Euclidean continuation. The fact that there's no conical singularity would probably say that this, if you translate to what this is, I think it would be that the surface gravity is constant, but I haven't checked that. But
Yes.
If there are no further questions, let's thank again.